Okay, so first I would like to thank the NOMAD team and all the organizers for bringing so many people together to have a look on how the NOMAD project developed in the last years. So as Luca said, we met already some 4 or 5 years ago, and I was at the TU in that time here in Berlin, and we started like the initial thinking about machine learning on material science data. As you see, I've moved to Charles University to Prague, and actually since October, so in a few days, I will move to the Czech Technical University. So in this sense, I like the word nomad, of like traveling around. So this really fits very well. So this is an outline of my talk. So in the time ago, in the 4 or 5 years ago, we were essentially thinking mainly about lasso and compressed sensing. So I will give some basic introduction to that. Since then, the topic of neural networks actually arrived on a pretty big wave of interest. So if time permits, I will say something to that at the very end, but I will also stress the main differences between these two things. So so anytime I have the chance, I try to propose that machine learning shouldn't be a black box. So if some math teacher nowadays would teach the kids in the school that mathematical formulas are completely mysterious, and you just play them as cards anytime there is some opportunity, and the guy with more cards and more formulas, it's the more mighty magician, it would certainly be one of the worst math teacher of nowadays. So I think we shouldn't repeat the same mistake with machine learning and not think about machine learning algorithms as some black box tools with the guy with the most black box algorithms in hand is like the most mighty magician. So I think it's really very important that when using the tools you try to understand them. So because of that, I would like to start with something very simple and which was essentially discovered 200 or 300 years ago. And that is what most of you are very well familiar with, and that is the least squares method. So we have a cloud of points in RD for simplicity, and we would like to fit some linear function or affine function. By this I mean just the linear function plus some constant, which would fit most of the data as good as possible. So as such, the problem is of course very easy, and we can have a look on the high dimensional variant of that. So let us assume that each of the points, which I call d1 up to dn, is described by omega numbers. So this would be the x-axis, which now has omega degrees of freedom. And we have capital N points in this space R omega. And naturally, we can collect these numbers into a matrix with these rows. And we've got some output properties. So that is what was on the y-axis on the picture before. So for each of these points, we have a real number, which should be the output. And we would like to have a linear fit between the inputs and the outputs, meaning the property P should depend on D by some linear function f. Well, there is not so many linear functions. Each of them can be written in such a way or in a matrix notation in this way. So we would like to have the coefficient vector C such that the P would be equal in the optimal case, or at least very close to D of C, and by that we actually have all the points included by this matrix notation. So in the optimal case, it should be equal, so you could get the solution just by this equation. Typically, as it was here, they wouldn't lie on a line, so there is no exact solution of such an equation. So we can solve it approximately, namely we would like to have the difference between these two guys as small as possible in the square, so that's what gives the name of the method. And we essentially look for the C which gives this quantity minimal. That's what I mean by this argument of the minimum. So we have a look where the minimum is attained. Well, you can imagine that with these 200 years old history of this problem, we know actually quite a lot about that. So there is a closed formula. You don't need to minimize anything. There is just a formula C is equal to something which involves P and D. Quite important thing is that this function is convex, which I will use later on for other problems. Typically, the C hat, so the solution of all that, would be fully occupied. So you will get a vector with all entries not equal to 0. And I didn't talk about that, but if you don't like linear functions, but you would like to have them affine, meaning linear plus a constant, you can just add once to your data, and the C, which will come to that column, will actually play the role of this plus C times 1. So there is a number of like simple tricks how to extend the method. Essentially the C, which is at the output, has the property that it minimizes this, but nothing else. This might be inconvenient in many situations. So for example, if the fit was achieved at the cost of the C having very large coordinates, so for example, 1 positive, 1 negative. So essentially the good fit of the data was achieved by subtracting 2 large quantities. At the end, this might produce a good fit, but it's like intuitive that it will be very numerically unstable. If you get out a bit of the area where the data was, maybe they wouldn't cancel that well anymore, and you would land up with essentially random numbers at the very end. So for these reasons, it might be reasonable, depending on the situation, not to minimize only this, but to minimize also the size of the vector C, of this coefficient vector. So you can combine these two things into such a formula. The lambda would be a positive real parameter, regularization parameter. And essentially it weights how important the fit is to you and how much the big coefficients C are like prohibited. And the good thing about that is without running any computer, without really having a look on the real data, you can tell very well what actually happens. So if the lambda goes to 0, this plays smaller and smaller role in such a case that at the very end you'll end up with the typical least square as it was before. And if the lambda goes to infinity, then actually this gets very large up to the moment where essentially anything non-zero here will kill this term, so you will end up with C equal to 0 at the very end. And the good thing about that is that you can really think about the problem and think about what it will do at the very end. So there is a couple of concepts which play an important role. One of them to mention is convexity. So to minimize convex functions is nice business in the sense the local minimizer is always a global one just by the definition of a convex function. So if a couple of people run the same program, they will really land up with the same result, which is obviously good. And there is whole books about, well, whole libraries about convex optimization. Libraries in both the sense of the word. So there is computer libraries and like the paper libraries full with information on convex optimization. So in this sense, to minimize convex functions is really a nice and doable job. The bad side of the story is if the function is not convex, it might be actually very, very difficult to minimize it. So in another area called computational complexity, there is 2 groups of problems which are called P or NP problems. The P problems are the ones which are solvable in polynomial time. So for example, minimization of a convex function. And then there is a class of problems where if you give me a candidate for the solution, I can verify if it is a solution in a polynomial time, but actually no one knows how to find a solution in the polynomial time. So one of 7, actually nowadays only 6 important problems in mathematics called $1 million problems is if these classes are indeed different. Actually, the common belief is that they are indeed different, but we don't have a proof for that. So if you land up in this NP class, it would be very, very surprising if some reasonable solution would actually exist. By the way, if it comes to big data, then polynomial is not really the end of the story. So if you imagine that your data is 10 to the 10 large, then the difference between linear or quadratic algorithm is huge. So the NP is definitely very bad, but being polynomial is not necessarily already good. So it depends then on the size of the data and the size of the polynomial. So what we might want to have, and let me motivate it by another story. So if let's say your points, they are typically some objects you are interested in. So in our case with Luca, these were some crystals. In some other applications, it might be patients, for example. And nowadays, you can measure a lot of data about crystals or about patients. I mean, there are so many machines taking automatically measurements one after another, meaning that each patient would be described by millions of numbers when it comes so far. And well, at the end, we measure everything which can be measured, but it doesn't mean that it has something to do with the output. So we are then interested about some properties of the material or some properties of the patient, which is typically being sick or not. And this usually is not connected with all the numbers we've just measured. So actually, we would like to know what to measure in the future. So we would like the method to select few of the measurements which were done, such that we do not have to measure everything all the time. So we would like to have the C, what we call sparse, namely the number of non-zero coordinates which really decide about the property, which really are connected with the problem, is actually very small. So we would like to measure everything, and we would like the machine learning to tell us what of that was really reasonable to measure and what we can actually forget about next time. So what we do, let us assume that actually only 2 of the coordinates play a role. And this means, okay, so let us have this 0 expression, which is not a norm, which is not anything reasonable, it's just a number of non-zero components, being smaller than 2. So among the 2 features which can describe the property at the very end, we would like to select the one which makes the fit the best. So among all the vectors which have essentially 0 everywhere up to 2 coordinates, we would like to minimize the least square error. So there is obviously one option how to do that. You choose all the pairs from 1 to D, and then you check how well it goes if you restrict your C to have these 2 non-zero coordinates. If you go with 2, it's well, essentially D squared of pairs. It might be already pretty huge, but if you go to triplets or quadruplets, it explodes very quickly. So this method is not really feasible, and as well, it's not then that surprising that the problem is actually NP hard. So this line, it's actually easy to write down. We would like to have this small and this small. Few non-zero features, good fit, that's exactly what we know. The bad answer is most likely no one can really find that effectively. So we just wished ourselves for too much. So the best way out, known since 20 years and actually known so far, is to do some feature selection, so to combine the best things from the known worlds, namely to do some convex optimization, but that one which also selects some features. And if you have a look on what we call LP norms, So for a vector c, you just sum up the coordinates in the p power and 1 over p. So for p equal to 2, you get just the typical Euclidean norm, which measures the size of the vector. Then here you see the unit balls, how they look like with respect to such a norm. So for p equal to 2, it's indeed the Euclidean ball. For p equal to 1, it's such a diamond, and it's still convex. So with every 2 points, it still contains the line connecting them. If the p gets smaller than 1, then actually it stops to be convex. These 2 points are in there, but the line connecting them is not anymore. So we just see that if p is bigger than 1, the problem is convex. If p is smaller than 1, it will turn out that it actually promotes sparsity, which I will show you next. So to take p equal to 1 is like to combining the best of the guys which we can do. And here you, well, see it from another side. So if the data giving the right measurements lives on this linear hyperplane, if we select the one which has the smallest L2 norm, meaning the smallest Euclidean norm, meaning the closest to the origin, which is here, we will land up with this point which has 2 coordinates non-zero. If of the same hyperplane we select the one which has the smallest L1 norm, this means we blow up this diamond which you had on the previous slide until it hits the line. So up to one line, which would be this one, it always hits this or that place first. So it always lands up with a vector which has 1 coordinate 0. The good thing about that is the picture is actually true also in high dimensions. So it's not cheating to show you this 2-dimensional picture and claim that with dimension 10 to the 10 it's still like similar. It's indeed true. So the idea of taking p equal to 1 was essentially by Tibshirani from 96, and it takes the very old Gauss-Legendre method with this L1 penalty term. So this name, lasso, comes from least absolute shrinkage, so this is minimizing the sum of absolute values, and selection operator. So Tibshirani obviously knew what the main property of this algorithm, of this one-line formula is, namely that it will actually leave you with a minimizer which has a huge number of 0 coordinates. So how does it look like? So there is what is called traceplot. So if you run this formula for different lambdas, so then you see that for some lambda, there will be like here 2 non-zero features. Here you see the sizes of these 2. You cannot really see from this diagram on which index they would be. To really see that, you need to have a look on the output of the algorithm. But there would be 2 features which would be non-zero and all the other zeros. If that's maybe too restrictive for you, then you go farther, and for the next lambda you might have 4 non-zero features, which already might be like better or still acceptable to you. So by plots like this, which you can produce by MATLAB nowadays easily with one command, you see which lambda to choose, because this would lead to the number of non-zero features which you aim for. So the good thing, which I like about that, and maybe you will like it as well, is that 10 years later, around 2006, a theory of compressed sensing arrived. And the aim of this theory is essentially to explain the nature of this L1 minimization. Oh, you can run it all the time. I mean, the computer has the buttons and you can push them anytime you want. And they will always find out something at the very end. But my aim here is to promote you to really think about that, and to really think about when it's reasonable to run it and when it's reasonable to expect that actually the outcome will most likely be of not much use. So we actually have a theorem, I will give you the authors later, which goes like that. So if the D, which I had on the slides before, is matrix with independent Gaussian entries, so you generate a huge number of random numbers, and the number of lines is large enough, I will get to that later, and there indeed was some reasonable linear dependence with an S-sparse vector behind, then actually this L1 minimization program, which just minimizes through all the U's giving the same measurements, the L1 norm of this, will actually recover it exactly, because there were these random numbers involved. It will happen only with high probability. So this is quite a strange thing from a couple of points of view. So first, it's random, so there is some probability of failure, but you are able to choose your epsilon to be, let's say, 10 to minus 10 or 10 to minus 20, and just neglect that. The good thing is it comes in only with the log. So even if epsilon is 10 to minus 20, it becomes 10 to 20. It seems too much, but then you take the log, and it's your friend again. The same is with the dimension. So the dimension might easily go to 10 to the 10. Then you take the log out of that, and it's again doable. And okay, there is this number of non-zero coordinates of the ground truth behind, which seems to be reasonable because you have S degrees of freedom, and therefore some S species of information seems to be unavoidable. So essentially we could live with such a theorem very well, but the first assumption is pretty deadly at the very end. So the D was actually our data. It was the thing we measured, the patients, the atoms, the crystals, and so on. And we replaced that with some random numbers. So that's not exactly what we wanted. So in some areas where you can design how you measure, which is, for example, the magnetic resonance tube, where you detect the cancer, you can like do some random vector orientation and measure different random directions there. But it's certainly not the case for something where the data was already taken or cannot be taken in such a way. So the good thing, so as such, the theorem doesn't really apply to real-life data. But nevertheless, I would like to claim that it still improves very much our intuition on how the things work. So first, here are the famous authors of the theory from 2006. And we can learn a couple of things out of that. So this is the best model we have so far. So the N should be that large for the thing to really work out of the box with one line minimization program. So if in the real life the data will most likely not be that good as the geometrical properties which are modeled by this, so essentially we have a bound like that if your data was selected carefully, it should be at least that number of patients or crystals. If it wasn't selected carefully, then might be that more would be needed. Second, the random numbers, I mean, it's a pretty deep geometry of high dimensional spaces. They essentially model uncorrelated objects. So if you select two random vectors in big dimension, they will very likely be nearly orthogonal. So there is mathematical quantifications of this. And this is really something to learn from. So if you can, then just select your features, your things which you measure in a very uncorrelated way. So for example, for this doctor experiment with the cancer, I would recommend the doctor to measure as different people as possible. So not to measure all people in one city of the same age, sex, and whatsoever, but to try to measure people which, by the numbers which you typically assign to them by the measurements, actually go as far from each other as possible. So to measure people from different continents, from different social groups, from different ages, and so on, in such a way that you really achieve a really broad spectrum of the data, exactly as the random vectors actually do. So that's essentially on the brief introduction to compressed sensing. So we wrote a survey chapter, which you can find even online somewhere. There is like 25 pages of introduction, so it's not that heavy and actually written for electro engineers to make it more like easy reading. So Luca asked me to say few words about dictionaries, so I made like 2 or 3 slides on that. So typically, the things we measure are not sparse. So if you take a photo, then each pixel is described by 3 numbers, and being all of them 0 just means that there was a black color. And in most of the features, most of the things you take a photo of, they wouldn't be all black. So that's not really the pictures you like, maybe up to some specific applications. It's not really what you wanted. But you can use the idea which is used in the JPEG format, and the JPEG format takes another orthonormal basis of the same space of the 16 million pixels. Most likely it's some wavelets or some discrete cosine transform, depending on the version of the JPEG. And then it transforms the vector into this orthonormal basis. And after that, the vector, the picture, the coefficients of it become nearly sparse, so there would be few coefficients which are large. JPEG would keep them, throw out the rest which was small, making a lossy compression which would still be very good. So essentially, if there is some orthonormal basis which fits very well your problem, in which your data typically looks much nicer and much more compressible than before, then actually compress sensing applies out of the box. You just rotated the problem. The geometry didn't change. So that is the easy situation. The more difficult one is the one which is also quite popular in signal processing. Namely, you have some dictionary, or let's call it lexicon, and denoted by capital L, which is a system of vectors in the right space, in the finite dimensional space, but it's overcomplete. So it has more elements than what the dimension of the space is. That's because your objects, like pictures, might combine more features, and you have one set to capture some of the features and another set to capture the other features. So you can imagine that on pictures with wavelets capturing the smooth areas and some curves, capturing the jumps of the picture. So if you have a look on a cartoon image, there is flat parts and edges. So if you combine all that together, you get an overcomplete dictionary. So it will have as columns important vectors of your space, so again R omega, but there would be more of them than just omega. So what does it mean? It means that, for example, if in R3 you choose 6 vectors, then everything is a linear combination of these 6 guys, but it's not unique anymore. You can write it as a combination of some of the 3 vectors or the other ones, and it's all doable. So the representation is not unique anymore as it was with the orthonormal basis. And the question is, what can we do about that? And the answer is yes, if you look for a while or ask someone, then you will find a couple of papers on that, with the first one being like, well, stating essentially this. Namely, yes, it's doable if you pose the questions reasonably. So if the representation, this C, is not unique, and X can be recovered as L of C1 and L of C2 from X, and anything which comes out of that, you can never recover the C1 or C2 exactly. The problem is just ill-posed. There is no unique answer, therefore you cannot find it. But you can recover the signal X, actually, or at least an approximation of that. So if you pose the question correctly and you are not looking to solve something which by its nature is impossible, then actually it still works. The bad news a bit is the error bounds, they involve what is called Gram matrix of the system. So this is mutual scalar products of all the things. So actually, again, if some of the selected 6 vectors in R3 are too similar one to another, then it still might be bad. So there is a couple of restrictions, but at the end they are quite reasonable. If 2 of the vectors are nearly the same, then you have hard time selecting one or the other out of that. Good news again is that this concept, without giving any details, got generalized to many other notions and settings. So for example, in classification problems, concept known as support vector machines got used in 90s and after 2000. And if you want to separate two clouds of point by some hyperplane which is orthogonal to some sparse vector, there is an easy recipe how to do that. You just have a look on the definition of the support vector machine and you replace L2 norm by L1 norm. A few minutes later you will find out that people did that, of course, already, because the idea is that simple nowadays. But actually most of what I've said before applies to this setting as well. It can be generalized to matrices, considering what is called nuclear norm. It can be generalized to functions by taking just the integral of the absolute value, which is a good analog of the sum of the absolute values of entries of a vector. So there is actually quite a huge amount of other situations where similar ideas and similar things can be observed, recovered, or applied. So if you see some paper where there is not exactly compressed sensing, it still might be very close to where it actually came from. So the good thing about the lasso, I believe at least, is that with the intuition gathered around, with, well, partially by the experience of running it a few times on some test data, or by the theory which tells you what should be correlated or uncorrelated with and how many samples you need, I can to some extent predict before you push the button if it's reasonable or not. If you have some problem, I can somehow think about how to prepare the data in such a way that running lasso could be useful. Recently, and I will get to the history, the field of neural networks actually well, became a pretty big fashion, and in contrary to compressed sensing, there is not much theory around, meaning mathematical theory. So I will come to that later, but when it comes to neural networks, unfortunately I cannot tell you like how many neurons to take or how to connect one with another in such a way that it's most effective. So let me browse through the notions and the history. So neural networks arrived very early, actually, already in 1940s, as a part of biological research. So essentially the task was to understand the human brain or human mind. It wasn't really to do some machine learning in that time. I mean, the machines of that time were, of course, not able to process bigger data. So it was really about like biological research, and what was known is that there is some neurons which are connected by some ways to transfer information from one to another. Okay. So essentially people draw a graph of neurons and connections in between them. To make it computationally feasible, there are no cycles. So you go from there and you push the information through the whole network until at the very end there is output. You don't run in cycles because it would be computationally pretty deadly. So you reorganize the neurons in such layers, and then the information in the input is somehow processed until it gets out at the output. So after this pioneering work in 40s, a number of different obstacles of both theoretical and hardware reasons appeared, which slowed down the field, and essentially neural networks were a bit out of fashion in 80s or 90s. And essentially the area of machine learning was taken over by lasso and support vector machines, which actually are quite easy to write down, easy to analyze, and easy to make some theory around. In 2010 and afterwards, so in the last years essentially, both advances in algorithms and in the high computational power, especially to use of GPUs, made it very, very attractive to use neural networks, which were actually quite large and could process a huge amount of data. Especially, they achieved human and superhuman performance in signal processing and in pattern recognition, which made it very, very attractive. And they could actually beat the state of the art as it was in that time, which essentially forced people to really have a look on that. Okay, so just a few words about what is what. So a neuron is essentially a function of this type. So this is a scalar product, this is a real number, and this is a fixed function, which is essentially a step function, like a sine function, or some smooth approximation of that. So the motivation for that is that it's like believed that the neuron sits there, it gets some input, and when the sum of the inputs weighted by some weights goes beyond some value, then actually the neuron shoots out some output. So it's really motivated by the biological considerations. And of course the choice of the activation function is like to be discussed, and the choice of the weights. So typically the activation function is just fixed by experience or by some of these formulas at random, and you only optimize through the weights, which somehow characterize the neural network. So you can think of them as essentially associated to each of these edges. Like the information from here going here gets weighted with some of these weights, and therefore there is the scalar product at the very end. So if you have already one neuron, then you can make more of them by having more layers out of them. So this would be your input, this would be the output, and then your model has a number of such things, such neurons in between, with many connections from left to right. And the question is, for example, how many of them you take. And to be honest, I'm not really sure if someone can really provide some like funded answer up to, we tried with 8, it just didn't work, so we tried with 9. I mean, maybe not the best answer you can wish for, but there is not really a deep theory which could guide you about how to design the neural network in such that it works for your problem. It's very often try and error business. So what happens, and you see it pretty clearly here, you've got some numbers on the input, they get passed to the first layer has some weights, each of the neuron, it makes some other numbers out of that, which then get passed to the second layer is doing the same and passes the output to the next and next and next layer until at the end of the day, we get some real number at the very end. So as such, there is a number of parameters to associate with such a neural network, namely all the weights and all the thresholds, which make the neurons fire farther and farther. So there is an algorithm, what is the training of the neural network? So there is some initial data provided in the beginning, and then you have some idea about what should be the outcome, and you try to fit the parameters in such a way that in the optimal case, the output of the neural network indeed coincides with what you actually measured or what the data was. So this is then processed through the whole network, and essentially you find a local minima in a huge non-convex optimization problem. So for a mathematician, this is nearly crazy. How to prove something about which essentially can run into any local minimizer. How to prove that it actually works if the output is not really prescribed and depends on the initialization of all that. So essentially, if two of you repeat the same, they might easily land up with a bit different result, and I mean that's pretty deadly for proving things. So Well, a bit of the history I said already. So indeed, the biggest breakthrough was achieved only recently with a lot of things and techniques used around. So without much detail, so the use of GPUs was pretty crucial in all that task for looking for local minimas. Neural networks turned out to be very sensitive to what is called overfitting, which is a general concept in machine learning. It means that your process was tuned too much to the data, to some tiny artifacts of the data, which actually would not be observed if the same data would be measured again. So essentially, it became too noise dependent on what your measurements really were. And there is again ways how to fight back, and combining all that, you can actually make this a successful story. It indeed is a successful story in the sense it was used in many different cases, for example, in the AlphaGo program of Google, but also on many, many other occasions. So up to now, the lack of the theory is, of course, at least for me, coming from the theoretical side of all that, really embarrassing. But they turn out to be useful. So although we don't have much intuition where to use them or how to use them, it seems to be like unavoidable to at least think about that if you really deal with some larger data nowadays. So, and with that, my time is over, and I would like to thank you for your attention.